And Greg is going to tell us about the Forward-Aperture extension.
Thanks, Josh. So thanks a lot for the invite. We'll just agree to the recording. Sorry, I have to agree to that. And then all right. So today I'm going to talk about a little pet project I was working on for the last couple of years, basically during the pandemic, which is this Forward-Aperture CMS extension with the idea to look for long-lived particles produced at the P5 or collision point of CMS in a very forward region. And as I'll show you, it's complementary to many other proposals which exist for LHC. But we believe we could have a fairly significant reach at fairly small cost, which differentiates us from monsters like Methuselah and bigger experiments. And essentially the name FACET stands for Forward-Aperture CMS ExTension, and that's how we position ourselves. So first I'll give you a physics case for FACET, then talk about conceptual design of the detector, influences and backgrounds estimates, and physics sensitivity studies, which is probably the most important part of the talk, and I'll conclude with some detector simulation fast and full detector simulation results, and talk about next steps. So essentially, as more and more high-energy data being collected and analyzed at the LHC, the high mass reach, as everybody knows, becomes saturated. You're running against steeply falling PDFs, and small increase in energy around 3 won't be really dramatic unless you're sitting right at the threshold of something like a black hole. So our best chance to discover new physics is perhaps to look at the places which haven't been explored before. Of course, it might not be there, but at least there is a chance. And this typically means low masses and low couplings. High masses and low couplings, of course, are also possible, but they're not likely to be accessible in the near future, maybe by the end of the LHC. Low couplings, of course, often imply long lifetimes, and low masses typically makes production in the forward direction, peaking in the forward direction. Thus, optimally, one needs to have a precision spectrometer somewhere forward in the forward region of big collider detector, for instance, CMS, i.e. far upstream. This, of course, has been realized by the HEP community at large and the LHC community in particular. There are a number of white papers and there are a number of proposals, beam dump experiments like an A62 sheet, central remote detector called XP, Methuselah, forward remote detector, phaser 2. So what we propose is essentially use CMS technology to build a particle spectrometer, which uses the same technology as CMS upgrade, about 100 meters from the interaction point on one side of CMS. And if approved, FACET will operate in run 4, 5, and beyond.
Could you quickly remind us of the status of the other ones?
So phaser is approved and it is running. They haven't produced any results. I heard that the background situation is much worse than they expected. Phaser 2 has not been approved yet, and Codex B, Methuselah is not approved, chip is not approved, and A62 is approved. There are more, obviously, experiments. I just indicated a few. There's Millikan, there's many other projects which look for specific cases produced at the collision points of main LHC detector. So there are several major advantages of FACET with respect to the competition. Most notably, the approved phaser experiment and the proposal of phaser 2. So most of my comparison will be basically against phaser and phaser 2. Actually, phaser 2, because phaser is not really a competition time-wise or sensitivity-wise. And a FACET will be fully integrated in CMS and can be used either together with the central detector if you have some good idea of something produced centrally and forward. I can give you one example of that physics. And unlike phaser, FACET is located around the LHC beam pipe, which on the one hand, of course, increases the background compared to being off-axis, On the other hand, it gives us unique physics opportunity. First of all, we could benefit from excellent LHC vacuum, as I'll show you, and to have a decay volume a la ship, which doesn't have any interaction whatsoever. And also look for unique physics processes not accessible for phaser. For instance, we could even do some standard model physics, such as where D decays, because D mesons are produced, charges produced enormous quantity of highly mass LHC in the region. So similar to the original ship proposal, FACET will have an LHC quality decay volume, which is about 18 meters long. That's as far as we could fit in this area, which allows to essentially background-free environment for the ALP sources, because we will be looking at the decay vertices deep in this vacuum volume. FACET will be built, as I mentioned, on the phase 2 upgrade concept, combining silicon tracker, fast timing detector, and HGCal type electromagnetic / hadronic calorimeter, which is basically electromagnetic and hadronic calorimeter built together with silicon technology. And we're also considering either gem type mill system or silicon mill system in a compact design. So important thing is that we are not inventing any new detector concepts or infrastructure, and we propose to benefit from the R&D of the current phase 2 and also the production capabilities. I'll show you FACET is about 5% in terms of number of elements of the CMS upgrade, so you will almost build it from spare parts. But in reality, you just produce 5% of sensors.
Would it be part of the CMS collaboration?
Yes, so we basically wanted to be part of CMS. That's why C in FACET is for CMS. We didn't want to go with phaser concept being a separate experiment. We thought it would be very beneficial to be part of CMS because we could benefit from the entire CMS infrastructure and the upgrade capabilities. And since we are not competing with the upgrade, essentially the idea is that you first produce full phase 2 upgrade, and then you just run your production lines for 5% more capacity to do this.
But you'd have your own author list.
Right now we have our own author list for the proposal, but it basically will become the CMS collaboration.
It will.
That's how we are trying to address this. So it will be really extension, just one of the sub-detectors of CMS, no different from, well, we actually have the model of PPS, which is totem, essentially joining CMS as for the products. So here is the schematics of the space where we want to install phaser. This is the sector 5-6. Here, this is what would happen for the high luminosity LHC. So they install a big superconducting dipole, D1, to separate the beams. So about 100, so as you know, the beams are focused, they collide at IP5, and this is the center of CMS. And then about 100 meters away, they are separated again and fed in the vacuum beam pipe. So this area between the D1 and a few more beam optics element and the taxon, which is the absorber for neutral particles, is essentially free. There's not much going on there. So that's where we want to install the detector. And essentially that gives us about 20 meters of space in the Z direction and about half a meter give it a take vertically plus minus half a meter. So that sort of defines the geometry of FACET. This is the area you see, it's pretty empty there. So here is the conceptual design of the detector. So here is the D1, this last dipole, and we plan to install additional shielding, which actually LHC people welcome because it would also help the taxon and just clean up the beams a little bit from all the albedo. Then we'll have a pixel, silicon pixel horoscope to beat any charged particles which enter the decay volume. And then the main part of the detector conceptually is this 18-meter beam pipe with the radius of the order of 50 centimeters, and we work with machine people.
I don't know what a hodoscope is. What's a hodoscope?
Hodoscope is just basically a matrix of scintillators so that you could look at the position of the charged particle, not just presence of the charged particle, but the position you could do it with strips, but then it creates ghosts, so pixels are a better solution for that. So essentially, as I will show you, we have about 30 charged particles per interaction entering the decay volume, so we need to tag them with this photoscope because we cannot video them, otherwise you would video every event, but we just need to know where the charged particle entered the decay volume so that we could work around this background. And then if the long-lived particle goes in, typically we are looking for neutral long-lived particles, so they are completely unbiased by the T1 or any beam optics. This is a straight section, so this is the end of the straight section from P5, so it just goes right through. And eventually it might decay inside the vacuum volume, and we could have, for instance, LLP decaying a pair of muons. And then what we put after this decay volume is the silicon tracker and timing, then this HG-Cal-like calorimeter, and the toroidal magnet, which is interspaced with the layers of silicon or gems for the muon detector. We need toroidal magnet because we cannot really mess with the beams, so we have to make sure that there is no magnetic field inside the beam pipe. LHC simply won't allow it, and that's why we need toroidal magnet rather than dipole. And then this is the shielding of the taxon, which is part of the LHC, high-loss the LHC.
So I guess the distance from the collision point is similar.
It's about 100
Methuselah?
meters.
It's similar to Methuselah, right?
Yeah, Methuselah would be about 100 meters above the
It's
ground.
a similar volume to.
No, the volume of Methuselah is size of IKEA, right? So it's a warehouse. It's much bigger, but the solid angle, of course, is much less here. But we are also looking at the different physics because Methuselah will look for the central production. We are looking for forward production. It will become obvious when I show you physics reach.
So wait, just one thing there. So you're in the LHC, you're expanding the LHC beam pipe?
Right, the expanding LHC beam pipe, and that might sound crazy, but this has been done actually. And so we talked to the machine people. There's no problem with impedance matching. You could do it either with concave type of leads on this decay volume, or you could put the wire mesh. And in fact, I'll show you the example of a lease beam pipe, which has about the same size as what we proposed.
Really?
Yeah.
That's 50 centimeters,
50
so a meter
centimeter.
across.
Yeah, so people who build missiles are very good at building these round things, which are
And it's made of.
it's made of steel. It's actually not very expensive.
You can match that to. Oh, it's all steel. It's not beryllium out there, anyways.
So you might have the thin beryllium window here, but that's it.
So something you break. So if something inside there breaks.
There's nothing inside. There's vacuum.
Oh, it's only vacuum.
Yes, it's only vacuum.
Right. You don't have any detectors in there.
Yeah. No, there's really nothing inside. That's the whole point. So
Okay.
vacuum cannot break, except for electronegativity.
Why not have a beam pipe, the standard beam pipe, but just put a separate vacuum decay volume outside it?
It is possible. We were thinking about this, but it's just as easy to do it like that. So we don't need to mess around, have extra material inside, because whenever you put the beam pipe, you would have to shield it out basically, impede somehow the interaction which might happen in the beam pipe. So there's no point. This is simpler than building the double pipe. And that's what has been done. In fact, at least a beam pipe was fairly inexpensive, was over 200K Swiss francs. That's not particularly big expense. So we submitted the paper on this conceptual design report. It was submitted on the 31st of December, but it was the first experimental paper of the year. That was intentional, of course. And you could look at some of the plots there, and I'll show them. And here's how we compare with phaser and phaser 2. So FACET, as you see, sits right here at the beam pipe in the inline with the beam, whereas phaser is somewhat off axis. So this is the beam pipe, so phaser is a few meters away from the beam pipe, like 10 meters or so. Conceptually, the phaser is sitting at the distance of nearly 500 meters. It has the radius of 10 centimeters for the decay volume, and the length of the decay volume is 1.5 meters. So those are the three numbers which you need to keep in mind when you calculate the reach. Phaser 2 upgrade is proposed to be at the same place. It's going to be 1 meter in diameter rather than 10 centimeters, and the decay volume will be 5 meters long. So this is, of course, a factor of 500, nearly 500 improvement over phaser, but you'll see that FACET, which has L of 100 meters, so the solid angle is 25 times bigger, radius of 50 centimeter, which is 25 times bigger than the original FACET and 4 times less than the original phaser, 4 times less than phaser 2, and decay volume of 18 meter would be very competitive, as I'll show you in the plots. And that's how the technology compares. So phaser is built of rather old technology. It has emulsion detectors for neutrino part of the program. Then it has the decay volume, which is essentially it's solid. It's not vacuum at all. So there's many interactions which might happen there. Of course, they have less background because they're sitting off axis. And then they have 2 meter long spectrometer with permanent magnets and the electromagnetic calorimeter and also scintillator counters for veto. That compares not to the scale because this is 1 meter and this is 18 meter here. This FACET, which you just saw, which uses all the fancy technology from the CMS upgrade. So the detector will have a radius of about 50 centimeters, and at 100 meters from the interaction point, this corresponds to angle of less than about 5 millirad, and pseudo-rapidity coverage between 6 and 8. Technically, there is no upper pseudo-rapidity cutoff, but because there is a 12.5 centimeter LHC beam pipe at the entrance of the taxon, we have to build detectors around this beam pipe, so we cannot cover radii below about 12 centimeter. Also, you'll see from the luminance plots that it's a very hot region, so you don't want to put detectors there. It's feasible to reduce this aperture despite beams being separated at this point. So if needed, we could further increase the acceptance, but it's easier to increase the acceptance by going slightly above 50 centimeters because you win on the large radius, not on the small radius. And data coverage is an order of magnitude better than for the phaser upgrade and similar to that of phaser 2 upgrade. The detector is shielded by about 30 to 50 meters of steel and all the beam optics in front of it, which corresponds to between 200 and 300 interaction lengths, which is actually better than phaser, despite the fact that phaser sits off axis, which only has about 100 meters of log. Yes?
So yeah, I'm wondering why do we need to expand the solid angle coverage? Because we only focus on the forward display.
No, because solid angle basically gives you the acceptance, right? Because the particles are produced in forward region, but they're not collinearly peaking at zero. They just basically more or less uniform in eta. So the more eta you cover, the more flux of the particles you get.
So you mentioned the phasers sees more background than expect.
That's what I heard. So that's the main reason they haven't been publishing yet. That they are trying to understand the background situation.
I see. Does the rumor include what it would be from the beam or cosmets?
No, I don't think it's cosmets. I think it's some beam halo of some kind. Lighting.
I guess the question would be whether that would be something you will be concerned about also.
Of course, that's the main thing, and I'll show you some of the simulation and what we expect to happen. So we hope that we could reach very low background, but if this is the case, basically the spectrometer which we built can identify E, mu, tau, and photons, just like big CMS detector. And the only thing is that our tracker would have to be 0 Tesla tracker because we cannot really put toroid nicely there. So this is simple for triggering. All the tracks are straight, but of course you don't measure the momentum of the particles directly in the tracker. You only measure the direction. So you have to couple with the calorimeter to get the resolution. And I'll show you how this works. Muon detector won't have this problem because muon detector is inside the toroid, and there you have about 1 Tesla magnet. And we could analyze the momentum of the muons. But for electrons and photons, it's a little bit more difficult. And rough estimate of the cost is about 5 million Swiss francs, which is rather modest compared to the cost of the CMS upgrade, which is about 100 over 100.
Always
million
good to
Swiss
put a big
francs.
number in the denominator.
And
Can't buy a house on,
size-wise, we're about 5%.
it's not even close to a house on Lake Geneva.
Yeah, it's close. On the lower side. So this is the Fluke Simulation which LHC people produce for us. And this is the neutron fluence and a short fluence and the muon fluence, which you could read all the axes, but just to give you an idea, we expect the detectors to get about 10 megarad of the integrated dose over the entire high luminosity LHC run, which is similar to what the central part of the CMS detector will absorb. So 10 millirads is around here.
Sorry, so what is Fluke?
Fluke is the simulation package which is used for all the radiation studies. So it's basically ray tracing of the charged particles with all the interactions in it. So that's a standard code which LHC uses for all the simulation for radiation background. So this is how the dose is distributed. And of course, once you reach taxon, the dose is very high, but we don't really have much. So we are sitting in this yellow region, which is about 1 megagrade. So just to remind you the technology which we are going to use, this is the main HG-Tau of CMS. It's essentially silicon sensors interspersed with various absorbers, tungsten steel. And this calorimeter has a very high granularity because of the silicon sensor. This is how this event, typical shower, would look at this calorimeter. So you essentially, I call it a PTA calorimeter because essentially you see every single particle, just like you looking at the PTA output, example you code painting, but that's essentially the granularity which we are going to work with. The vacuum tank here is the beam pipe of Alice right here. So it has basically the same size as we need, and it's slightly longer than what we need. So this is 23 meters and 40 centimeter radius. The cost was 250 Swiss francs.
Why does at least need a big beam pipe?
They need beam pipe to essentially separate the beams to decrease the background. So that was installed before.
Oh, they have a bigger crossing angle?
So now let's talk about the most interesting thing, the physics reach. And essentially, conceptually, for LLP decaying within the FACET vacuum volume, the figure of merit, which is 3 or 5 signal events, whatever you want to use as the discovery or limit potential, depends primarily on the product of gamma C and lifetime tau. And here is how FACET compares with phasor and phasor 2 in this figure of merit. So this is gamma C tau, and these are some arbitrary units. Well, it's decay factor times solid angle, but you don't need to worry about actual numbers. You could just compare the line. This is how phasor looks like. Expectedly, it peaks at about 300 meters because it's about 500 meters away from the collision point. Phasor 2 has peaked about the same position. Of course, phasor 2 is a couple orders of magnitude better just because of the size. And this is how the figure of merit looks for FACET. It peaks much earlier because we are sitting closer, we're sitting at 100 meters. And the solid angle is much bigger, so that's why your sensitivity is much bigger. So we are essentially on, there's no competition for low gamma C tau up to, I don't know, a couple, 20, 30 meters. And at large C tau, we actually will be doing about order of magnitude better.
What's the cost of phasor 2?
It's a well-hidden number. Jonathan, I think, actually got mad at me when I cited it. It's about $20 million. And he asked me where I got this number, and I gave him reference to his own paper. So in 2000,
Phasor 1 was like 1 million.
No, but it's you know, it's 100 times bigger.
Is it?
Was Jonathan suggesting that that 20 million number is out of date and they're going to do better than that, or?
I don't know. I think he forgot that this number was actually put in their paper, but things only get more expensive. So as they learn about the backgrounds, they probably would need to have bigger technology. But I don't think they could build it for anywhere close to like the specs. I think it's going to be really high.
You mean just because of the size of the?
Just because of the size of it. I think just the amount of instrumentation more or less scales with the volume. Okay, so basically, in order to compare things fairly, we took a few examples from Phaser physics book, which they did really a wonderful job on looking at the sensitivity. And we decided not to go for all the examples they have because you will see more or less uniform picture for each of these type of physics, because it really is all basically based on this plot I showed you on the last slide. And we look for dark photons, dark Higgs bosons, heavy neutral leptons, and ALPs. And I'll show you each for all of these things. In addition, we could also look for perhaps for rare D-meson decay, for instance, lepton flavor violating decays, strongly interacting dark matter, and some standard model topics, but we haven't been really pursuing this yet. We really focus on the new physics which are LFP. So given the 8 range of FACET, the main production mechanism for light LLP, just like in Phaser, are various meson decays. And for instance, pi 0 and eta could decay into photon and dark photon by kinetic mixing, and that's how we produce a large flux of the dark photons in the forward region. We could also look for heavier decays. For instance, if you look for dark Higgs, it would be coupled with big quarks, and you will look at the B meson decay, B to S transition with the single or pair of dark Higgses, so B to K pi, for instance. And for the heavy neutral leptons, we could use charm and BDKs as the source, just like normal semi-leptonic decay, except that you replace neutrino with the heavy neutral lepton. And in this case, we only care about the LLP part of the decay chain and needed to subsequently decay within the FACET volume. We assume that if the particle decays in the FACET volume, since it's very forward aperture, it essentially will be detected. So in all these plots, we assume 100% detection efficiency, which of course is not the real case, but that's the benchmark which Phaser uses and everybody else uses, so that's just for fair comparison. So we typically ask for either 3 events or 5 events, assuming 100% efficiency, given that the decay is within the acceptance of the detector. That's the rule of decay. We could also produce LLP by different mechanisms. There is a dark Bremsstrahlung, so you could actually coherently emit dark photon from a photon. There is direct dark photon production, which is similar to direct photon production. And there's Primakov production for ALPs of nuclei. Also, there's a Drell-Yan production, of course, but it's hard to compete with LHCb and Atlas and CMS central detector because you see that the cross-section of the Drell-Yan in the forward region, which is this lines, is much suppressed compared to the central production. But I will show you some example where we actually use Drell-Yan production. So mainly to estimate the physics switch, what we do is basically what Phaser did. We generate the map of various decays with Pita, various B mesons, B mesons, pi mesons, eta mesons. And all we need is the 2-dimensional plane, which is the angle versus the momentum of the particle. In this rapidities, we don't really care about PT. Everything is about momentum. Momentum just gives you a gamma factor, and angle tells you where in the detector you are. And this is what FACET covers. So it's 5 meter rad, and well, this is what Phaser and Phaser 2 would cover. So FACET has a little bigger solid angle because of the radius and the position. And then we could just simulate various decays. This is just the toy simulation where we show what is the momentum spectrum of a typical dark photon. So for 300 MeV dark photon, which would be producing 8 decay. It peaks at about 100 GeV, so it's a fairly energetic photon. And the polar angle is about 1 millirad, so it's fairly well inside the facet detector. And this is the number of events in 3 reverse autobar, which we get as a function of, say, C tau. And basically, you cut at 3 or whatever you want to get the sensitivity. And then you basically take the sensitivity in terms of C tau and convert it into whatever parameter of interest, the kinetic mixing or any other mixing angle you want to deal with. If we look at the dark Higgs with, say, 3 GeV mass, which will be producing B meson decays, then the spectrum is even hotter. It's about 250 GeV. And the polar angle basically is much more flat. But again, with 5 millirad, which is the edge of this curve, we cover a rather significant fraction. And that's how the number of events looks like for the dark Higgs. So we were working with all this simulation and developing our own simulation, and then Felix Klink and Sebastian Trojanovsky made this nice package, which basically was what they were doing for Phaser, and they made it public. It's called 4C, Forward Experiment Sensitivity Estimator, and it's available as a public code. So we immediately took it and basically incorporated facet model in 4C. So most of the plots I'll show you actually comes from 4C, which is very nice because that also allowed us to immediately compare that we could reproduce the Phaser 2 curves directly. So we know that it's running correctly. So let's go and look at the physics speech for different particles. So these are the dark photons. Essentially, we look at the pseudoscalar decaying at the photon and dark photon, and it's proportional to the kinetic mixing squared. So the figure of merit is the kinetic mixing squared times C tau, and that's how it looks like as a function of the mass of the photon. And this is how the sensitivity compares. So the things you want to look at are Phaser 2 in red and facet in blue, and you see that we have nicer reach over the entire range of dark photon masses, with the caveat that it might be hard for us to go below 100 MeV from the background point of view, but this is anyway the case where the beam dump experiments have much better sensitivity, so we want to push it out to the higher masses, which is done by dark Bremsstrahlung, and here you see the low peak, so that's sensitivity increases. But basically, just from the solid angle, you see that facet wins over Phaser over the entire plane. More dark photons. So this is a specific model which you could look up in this particular paper. This is a hidden sector which has a couple gauge bosons and dark fermions. So here there's additional production of dark photons from the dark fermion Bremsstrahlung. And wonder how viable this model is, but it's just to show you that you could actually reach higher masses. So what they did in the simulations, they compared Phaser 2 with facet, and you see that facet would go to much higher masses, about 10 GeV in the dark photon mass. And what is labeled as MTD here is the mid-timing detector of central CMS. So that shows you a nice complementarity of facet and central production. Majorana, of course, again in the central region, but there is a nice gap here, which facet could cover. Metusla could do even better because of the bigger volume, but hope to be there first. The other interesting process is the dark Higgs, and here is, I'll show you two cases. One is just the standard case where dark Higgs is produced in B meson decays, B to S side transition, and it's basically everything depends on the mixing angle data. And here you see facet in red versus Phaser 2 in green. Again, you see similar picture as for the dark photons. We are going all the way to the kinematic limit. This is just the mass difference between B meson and K meson. We cannot go beyond that. but you could go a little lower and a little higher in the mixing angle of the entire plane. But the real killer case is the dark Higgs with trilinear coupling, where in this model you could actually have the Higgs H125 decaying in a pair of these dark Higgses. And that gives you additional source of the production process, just the large number of Higgs bosons produced at high luminosity LHC. And it also gives you another source of the light decays. P meson could now decay in a pair of dark Higgses rather than a single dark Higgs. And basically, we incorporate both these cases, the three-body decay of P mesons, which enhances sensitivity at low masses, and the Higgs decays, which enhance the sensitivity at high masses. And what was noted back in 2019 by this paper, which not many people know, some obscure Russian paper, is that it's actually interesting that when the decay of the Higgs boson in a pair of these phi dark bosons, this happens at rest, meaning that the basically you are very close to the kinematic limit. Then all the particles are really boosted forward, and there is enough forwardly produced Higgs bosons at the LHC apparently to have a significant flux of these dark Higgses in the forward direction. And that's exactly what we see. So if you here you see a really drastic difference between FACET and Phaser 2. Phaser 2, essentially, the sensitivity drops at about 3 GeV. Those are all the dark Higgses coming from the Higgs boson, from the meson decay, except that they have this tiny little sliver of space right around 62.5 GeV. So if decay is right at rest, they have just a bit of sensitivity to get it. For FACET, because the phase space is much bigger, we cover this entire sliver of parameter space. So that's a killer case where you actually have sensitivity from, which is unique from about 30 GeV all the way to the kinematic limit for the dark Higgs production. So that's one nice case where which we identified, and that would be also a case where you could actually use central CMS detector, because for instance, if you want to look for BBF production of the Higgs bosons, you could tag these two jets in central CMS, which would reduce background by dramatically.
Do you have a plot like that?
No, we don't have plot like that. And another case which was done by Suchita, who is also part of our little collaboration based on her earlier paper, is the case of heavy neutral leptons, which are produced by light Z prime. And again, this is Phaser 2 versus FACET. You see that for the Drell-Young production, Drell-Young light production through the Z prime, FACET could actually go all the way to 20-25 GeV in terms of coverage. And Matusla would do better. Again, in Drell-Young, we cannot compete with central production, but we are fairly competitive with LHC, for instance, and that unique sensitivity with Matusla in certain space. And the final case which we studied is the ALPs. So here we did the ALPs with dominance. So basically, this formula Lagrangian just coupled to W's. The original motivation was to explain Coda anomalies, 3 events with K to pi nu, which they observed, and that was the model by Stefania and company. And this can be produced in meson decays or via Primakov effect. And basically, this is FACET, Phaser 2 versus FACET. And by now, from comparison of all these plots, except for the Higgs one, you see that the picture is more or less uniform. So you get about a factor of 2 larger range in terms of the couplings or mixing angles or kinetic mixings compared to Phaser in the entire phase space. And we typically push things a little bit beyond in terms of the math. So at that point, we decided it's enough for us to do these physics cases because they all are more or less telling you the same story based on the acceptance. So finally, just a few plots on how we could reconstruct the events. This is still based on toy Monte Carlo. And for instance, typical configuration, we would try to reconstruct is this LLP, which enters the decay volume and decays, and we see these two tracks in the tracker, and then whatever happens in the calorimeter. So this is pointing resolution in Z, so how well we could point things back to the decay vertex, so that we know that it's originated far from the boundaries of the volume. And assuming 30 micrometer heat resolution, which is typical for the silicon detectors with 100 micrometer strips, the Z resolution is actually very good. It's a few centimeters, couple centimeters, so we really could pinpoint the location inside the decay volume fairly precisely. So depending on the opening angle between these two tracks, that's the signal which we could achieve. And here is the use case where we use calorimetry. So for instance, for decays in the electrons, dark photons or ALPs decay a pair of electrons, we get the directions from the tracker with the resolution I showed you, and then we get the energy from the calorimeter. And basically this is the mass resolution for the parent particle which decays in a pair of electrons. And you see that this was 300 MeV dark photon. So you see that the resolution is about 7%, which is not bad.
So what's the momentum of these electrons?
So typical momentum, I showed you the momentum of the LLP. So electrons will be half of this. LLP peaks at about 100 GeV.
100 GeV.
So you have 50 GeV electrons. So those are
Right.
nice electrons we can start
Right.
figuring
That's
out.
nice to be far forward.
That's right. Yeah, because it's P. No one cares about PT.
Right.
PT is tiny, but we really not interested in P. If we only have photons, we also could actually do pointing, because the HG having this enormous granularity allows you to actually see how the shower develops and point it back. And this is the simulation for CMS phase 2. You see that the resolution in eta, well, they are talking about eta because that's still fairly central production, eta of 1.5, 2.5. And you see that the resolution in eta is about 2.5%. It's easy to convert this into resolution in theta. In fact, resolution in eta is just absolute resolution in eta is the same as the relative resolution in theta. So delta theta over theta is about 2.5%, which means that for a photon originating, say, 10 meters upstream, right in the middle of the decay volume, we could point it back with the resolution of about 25 centimeters. This is, of course, much worse than a few centimeters from tracking, but still, we could easily lose only 1 meter on each side of the decay volume in terms of Z, and be sure that the photon originated deep inside the vacuum, like what's And the backgrounds, essentially, what Phaser assumed in all their studies is that this is a background-free situation. This is the theoretical approach. Experimental approach is to reach this background-free situation. That's what they're working now. In FACET, we hope to achieve the same. And we started investigating main backgrounds, which we believe would come from long-lived neutral particles such as K-shorts, K-long, and lambdas. They all secondary produce, because all of those which are produced at 0.5, they never reach FACET, they decay much faster. Essentially, we started estimating the flux using Fluke. We believe that most of these decays could be dealt with. In particularly, we started looking at K-short and K-long decays. K-short decaying in a pair of pions. We could reconstruct this by detecting pions in the calorimeter and running calorimeter in this case, and seeing two tracks in the tracker. And this is the resolution we get for the parent mass. You see that it's not bad at all. We achieve about 5% resolution, which means that above, say, 0.6 GeV, we probably are fairly safe against this background. So that's why I said that lower mass reach may not be possible with FACET, but the idea is actually not to look below a couple hundred MeV, but move to above GeV range most interesting stuff would happen, which is uncovered by the present generation of experiments. Lighter masses typically are covered by beamed-up experiments very well, so it's hard to predict this anyway. But we may be able to actually also work around it to look at smaller masses than 400 millimeters. So that remains to be seen with detailed simulation. And some ideas of how to detect strongly interacting massive particles. So in this case, essentially, you want this particle to penetrate the shielding. So that's exponentially falling. So this is the probability of penetrating, say, 53 meters of steel, which is about the size of the beam optics, which is in front of the FACET detector. And then you have falling probability of interacting within 2 meters of steel, which is the size of our calorimeter, HL. So you want them not to interact with the shielding before, but still have enough events which interact in the calorimeter. So if you multiply the two, you get more or less flat efficiency of the order of 1% over rather large ranges of interaction lengths of these particles expressed in meters. So that's just the strength of the interaction of the SIMS. So we haven't done detailed simulation, but just there is an idea that with about 1% of acceptance, we would be sensitive to SIMS if we somehow manage to uncover these decays without the background. And we haven't really used the time of flight for the studies I showed you, but we could use it as an additional handle. We could actually see that particles come from the 0.5 and not from the shielding or secondary production. This is basically how many, what is the delay in terms of the picoseconds for particles of different masses as a function of the momentum, whether they come from the collision point or somewhere closer to the detector. So we could, in principle, resolve even calculate the mass of the particles using the time of flight as an additional handle. Yes?
Can this experiment also be used to detect the miniature?
That's my next slide, I believe. Other physics topics, yes. So indeed, we could try to detect newly charged particles because we have a number of silicon planes and also HG. And this, in fact, is similar to the phasor proposal for Formosa, which is a couple of years ago. We haven't studied this in terms of sensitivity, but indeed that should be as possible as Formosa as a part of phasor. And we could also study some other physics topics. So basically, there's, people come with different ideas. We have a very small group of people working on this, so we don't have real CPU cycles, brain power to pursue all of them, but essentially, we probably won't be able to do neutrino physics because this is not an emulsion experiment. The background situation is too high. We cannot do magnetic tracking because of the beams. We cannot distort LHC beams. And there's also obviously constraint of the cost. So we didn't want to kind of overcreep this mission and wanted to go with the simplest detector. But as I showed you, we have rather huge sensitivity to different processes. And if we can reconstruct taus, that would be even more interesting because phasor cannot really reconstruct tau decays. Using the CMS technology of the calorimetry, we might be able to do that actually quite well. And we could, as I mentioned, we could do some standard model physics, say forward meson production, where we use D1 as the analyzing spectrometer, which is a Tesla magnet right in front of us. Use it to deflect the particles and see these decays from the D mesons, which normally go through the beam pipe.
So I had a question on the last slide and on this slide. So so what part of the detector are you getting the timing from?
So the timing, there are two parts. One is the silicon tracker with LGATs. That's just like we have the mid timing in the forward direction for the CMS proposal. And the second one is HG itself. HG itself, it has built-in timing capabilities with 25 millisecond resolution.
by itself is 25?
Yeah.
Okay.
No, for energetic clusters, but energy is
Right.
not an issue here.
Right, you have a lot of, and then, so you're saying about the millicharge thing, so you can run the silicon, what, at a higher voltage or a lower threshold or something?
No,
to
we
be able
just
to
have
change?
plenty of silicon. We could remember this HGCal is a tracker, right? It's a tracker with absorber plates.
You don't mean the tracker, you mean the calorimeter.
Right.
But now there's less of a distinction
Exactly.
between.
Right.
Okay, okay, I see what you're saying.
So we could actually even maybe not see it in the tracker, or see very faint signal in the tracker, and then see something in the calorimeter which resembles MIP.
Right, you'd have to run under some different conditions for the detector than, I guess,
I'm
the
not
normal.
sure we need different conditions.
It's a very small energy deposit.
Well, yeah, I mean, it clearly depends on on how close to milli you want to get. By millicharge, I don't literally mean millicharge. We charge less than 1. So we haven't really studied it, so I can't give you an honest answer. But surely people have some idea. We could have special run with different detector conditions. One could also do a lot in the low luminosity runs, like heavy ion running, because their background is literally 0. And certain things like, with heavy ion, you could have free basic neutrino LHC in the photon collider. So anything which is produced in photon-photon interaction would be studied. So that's another idea. And of course, we haven't fully explored the idea of simultaneous triggering with CMS. But given that we use the same trigger technology, we basically send our data to CMS, so there's no problem in simultaneous triggering. We have use case of PPS detector at the total, which is 200 meters upstream, so there's absolutely no problem in triggering together. But main physics problem is standalone triggering, because you don't really have anything in the central detector, just a bunch of mesons. And that's more or less it. We started putting this thing in the full GN simulation. So that's the beam pipe, the HGCal, and so forth. And yeah, so that brings me to the conclusions. So we believe FACET would significantly enhance the capability of CMS for long-lived particles with these masses and these lifetimes. It's based on the same technology as CMS detector, which is good. Sensitivity rivals phaser 2 upgrade, and it's unprecedented for gamma theta over the order of 100 meters. And we're working on detailed layout. We obviously have the presentation, the collaboration. Many people thought it's an interesting idea, so we are going to submit a letter of intent to CMS, official letter of intent this summer. We just published this physics reach paper, and we have a core group of about 15 people working on this as a pet project, and about 30 more people who expressed interest but didn't have much time to actually contribute yet, so that hopefully will change. And of course, anyone who wants to collaborate from the theory world, experimental world, very happy to have you on board. Thanks a lot.
But you'd have to be on CMS.
This just benefit.
Okay.
So as I haven't thought about like these sorts of analyses, how similar are the analyses that you do to like standard, CMS analyses in terms of like identifying objects and
many of the
cutting, or
techniques,
are they more inclusive? Are they similarly? I mean,
I mean, this is more like B physics in CMS, which is, we are not designed for B physics, but we could do B physics. We don't really have good particle ID here, but on the other hand, particles we deal with are the same particles we deal with central CMS, so it's the same technology, same reconstruction. So things like distinguishing two close biphotons is a standard thing which CMS does in the central region. Identifying taus is standard thing, electrons versus photons, muons. So most of this would be common, but of course backgrounds are completely different, so one has to see how to deal with that.
but how model dependent? I guess my question is sort of like, if you have a signal which is different from, but kind of not totally different from the ones you're looking for, are you likely to see it, or do you really need to have?
No, I think you're likely to see it, because basically what we're going to lose. So I'm thinking of basically in terms of triggers, because that's what we're going to trigger on, that's kind of what kind of physics we will cover. And we are going to trigger on something like 2 tracks, which point somewhere inside the vacuum volume, or 2 tracks in the calorimeter deposition, or just large calorimeter deposition. So triggers and the rate we expect will be fairly small for that, so there's no problem with triggering. It's a background low estimates, but we easily fit the CMS trigger bandwidths in high luminosity LHC will be increased by a factor of 10. It's about 750 kilohertz, so it's close to megahertz. You could easily feel 5% of it without a detector, without the lowly data budget. And so that basically tells you generic things you could look for: 2 calorimeter clusters, 2 tracks, some combination of thereof. So I would say it's fairly generic for 2 muons. We also have some ideas of looking for 4 tracks, because that's much less background than certain models where it's cascade decay. Yes.
For particle ID, did you consider Cherenkov detectors?
No, we don't have any Cherenkov detectors. Basically, because we don't really need particle IDs, I think, because the only hadrons we're interested in are really pions, and pions are so much more ubiquitous than kaons that having kaon-pion separation probably won't help us. But also think about this momenta. We're talking about pions with momenta of 100 GeV, and no Cherenkov detector will allow you to separate kaon from pion at these gamma factors. I mean, there are Cherenkov detectors, but they're 20 meters long. But it's not like a really Cherenkov. So no, we don't think that particle ID would be particularly beneficial.
Are there any measurements of the backgrounds in that area, or just?
So that's what we want to do for run 3. We hope to put some scintillating counters there to get some radiation measurements to validate Fluke model. But from Fluke people, we know that they're good with a factor of 2. So all their simulations they have done so far agree with the measurements with a factor of 2. It's reliable. But yes, of course, it's nice to have measurements.
Is Fluke used for phaser?
Fluke was used for phasing.
The fact that their background is higher than expected.
No, the backgrounds come from Halo, which is hard because they are far from axis, right? So they're 10 meters away. Fluke, I mean, the model which they put in Fluke, they really focus on the central location, so they might not be very accurate in large angles, right? So it's
I mean, most of the Fluke stuff, it's like low energy neutrons and photons, right? It's not what you care
no,
about.
they have kaons, lambdas, they have all the modern Fluke.
Right, but most of the radiation dose.
Yeah. Right.
So what they care about simulating correctly.
They care about neutrons much more
Right.
than other stuff, but they
Right.
also have fairly. So basically, they gave us list of particles with their momenta.
But nobody's ever measured the kaon
Nobody ever
background anywhere
measured.
at the LHC.
That's
right?
true.
So
Yeah.
you know, in addition to simulators, you want something that can measure like a track. Like how often do you get a track?
Right. That would be hard to install in round 3, but maybe.
It doesn't have to be silicon. It could be
No, it
small
could be just small
simulators,
tracker or something, right?
a hodoscope, you know, but with small,
Yeah.
good, decent granularity.
No, that's a good idea. Maybe we'll ask you to put
I
milligram
have
there.
one. I have one.
Good.
When is
CMS?
LS3 again? Just
LS3 is the next shutdown.
before High Lumi?
For High Lumi, right?
When does High Lumi start again? No.
So 26,
26.
27 maybe. So
And-
26 is when they shut down, so that starts around 28.
Starts in 28, and then this would be running then. That's the
No, so our goal is to sneak in the bin pipe during the LS3, because that's a big thing where you need to break the vacuum and so forth.
and then you're taking
And,
data.
and
with-
then putting the detector is all clamp design, so you could do it in small, like small technical stuff. So putting rather small pieces of equipment there is not very hard. You don't need to break vacuum or anything like that. So our idea is to, well, on the one hand, it's a very delicate situation with funding, because as you might imagine, both Atlas and CMS upgrades are running out of money. They're overspending, and the pandemic didn't help. And so CMS wants to make sure that this does not compete at all, either money-wise or time-wise, with the main upgrade. So we are now pursuing totally different sources of funding, similar to what Taser did, go to Simons and other places, so that they're not really DVE or NSF money, which would be a clean way of saying that this is not competing, because funding comes from a different envelope. And at the same time, depending on how upgrade progresses, we may not be able to produce the detector until the phase 2 is ready, which means that we'll probably miss the first year of operation in round 4, since we'll be producing detectors, but we'll install it somewhat later.
You don't want to go too much later because you lose the
We don't want
luminosity.
we lose the luminosity, but as usual, things are ramping up. So first year we probably won't get too much luminosity. But the main make or break for us is to install beam pipe in LS3 rather than LS4.
And if Phaser 2 is funded, their schedule is
Phaser 2 would be on
Running
the
with
same
them,
time
yeah.
scale, yeah. For them, it's easier because they don't have a problem of breaking vacuum. All they need is money. Give the bigger detector.
But see, if you had your separate vacuum, then you don't have to be tied to that schedule as much, right? You could put in your own thing before.
In principle, yes. So that might be a possibility. We have to see. Problem is that,
You won't have the detectors anyway.
right. It might be possible, right? So the benefit of the having LHC vacuum is that we don't need our own vacuum pumps and cryo and all this stuff. So it comes for free, and that's the big benefit. I'm not even sure there's space there to put big enough pump to actually create high quality vacuum in this rather large volume. That's why our main idea was just to piggyback on the LHC, since at least did this. So far, LHC people didn't say that this is impossible. So that's a great idea.
Any more questions?
Yeah, so can I ask what's the projection of the FACET on the mini charge particle?
Yeah, we haven't really studied this, so I cannot really tell you.
So do you have any expectation of that? Like how does it compare with like experiments of Formosa or Millikan?
Well, Millikan is quite different, but Formosa would be similar in concept. They use different technology, obviously, but as I said, we really just didn't have any chance to do any detailed simulations, so I don't want to do animating. But given the parameters, it's pretty easy to estimate. So basically, the idea of this paper we put out is to put ourselves on the map so that different pheno people could do this type of simulations and look for each task. If there's some great ideas of what kind of extra detector we could put to make it better for mini charge particles without breaking the bank, that's certainly a possibility.
No questions?
Thank you.